Thank you for joining this lesson. We're going to discuss radioactivity, number 13 of the paper, whereby we are told in part A to differentiate between nuclear fusion and nuclear fission. Remember to subscribe to this channel and to also share the link with friends. Nuclear fusion is the fusing together of light nuclei to form a heavier nucleus. So the fusing together of two different light nuclei to form one heavier nucleus is what we call nuclear fusion. Then the nuclear fission is the splitting of a nucleus to form two different nuclei. Part B, we are told that the equation below represents a nuclear reaction. So we have a certain element here. I can propose it is a polonium according to the formula. So polonium is having a mass number of 218 and an atomic number of 84. When it reacts, it gives us a daughter nuclide, which is named A. Then now it is having 218 as the mass number, which means mass number has not changed. But the atomic number becomes 85, which means it has increased. Then plus a certain radiation which has been emitted. We are told to identify or to determine the values of P and Q. So both sides of the nuclear equation or nuclear reaction are supposed to give us the same atomic numbers and the same mass numbers. Therefore, for us to get P, we are supposed to equate 84 and this side. So that we say 84 should equal to 85 plus P. So the value of P is going to be -1. So that when this side is added, we will get back to our 84. The other one is Q. We should say the two sides are supposed to be the same, but because the mass number is not changing, it means the mass number for the radiation which was emitted is just 0. Therefore, we can say Q equals a 0. Identify Y. Which particle has been emitted such that when we write it, Y, we'll have 0 and a -1. So this one is an electron, and the loss of electron is what we call beta radiation. So it is a beta particle. Which is an electron, basically. Beta particle. It's a beta particle which can be written as beta particle. So it's a beta particle or simply an electron. We are told in another question that the figure below represents deflection of various radiations from a radioactive source S. Placed in electric field between plates X and Y. Plate X and plate Y. Whereby you can see this one is positive. This one is negative. Then the radiations are here. M, P. This one is not labeled. We are told to identify the radiations marked with the letters M and P. So when you try to observe here, you see that M is being attracted to the negative plate of an electric field. So if it is being attracted to the negative, it means itself is positive. Therefore, M is going to be alpha radiation. Otherwise abbreviated this way, alpha radiation. And P, which is being attracted to the positive, it means it itself is being negative. Therefore, it's beta particle, beta radiation. Abbreviated this way. That is beta radiation. It can be explained further that the radiation P is being attracted so quickly. The deflection is being so quick. And this explains further that beta particles are lighter than alpha particles whose deflection is a bit small. They are not highly deflected like these ones. So these are alpha particles which have a bigger mass, or they are a bit massive compared to beta particles. Let me go to part D, whereby we are told that a sample of radioactive substance initially has 8 times 10 to the power of 25 particles. The half-life of the sample is 98 seconds. 98 seconds. Determine the number of particles that will have decayed after 294 seconds. 294 seconds. Let me approach the question using two methods. We have the decay formula, which says that the remaining number is equal to original number multiplied by half, which is raised to n, where n is going to be total time out of half-life. In other words, n is the number of half-lives. So we can say the remaining number which is unknown is going to be original 8 times 10 to the power of 25 times half raised to 294 out of 98. 294 out of 98. So when we take 294 and we divide by 98, 294 out of 98, I'm getting exactly 3. Therefore, this is going to give us n as 8 times 10 to the power of 25 multiplied by 1 power 3, because this becomes 3. So 1 power 3 becomes 1 out of 8. 1 out of 8. Therefore, we can say the number is, when we take 8 times 10 to the power of 25, then we multiply it by 1 out of 8. This gives us 1 times 10 to the power of 25 particles. Otherwise, we can follow a decay series whereby we say, we want to see the 3 half-lives, because 1 half-life is 98 seconds. So alternatively, we can see the three half-lives where they will take us. Originally, we have 8 times 10 to the power of 25. In the first half-life, because half-life is the time taken for radioactive substances to reduce or to decay by half the original number. So after 98 seconds, we're going to have 4 times 10, 25 particles. After another 98 seconds, we shall have 2 times 10 to the power of 25. Then finally, after the last 98, we shall have 1 times 10 to the power of 25 particles. Therefore, we can see when we have 98 plus 98 plus 98, that gives us the 294 seconds. Therefore, after 294 seconds, which is 3 half-lives, we're going to land at 1 point. 1 times 10, 25 particles. Remember, these are remaining particles, but the question is telling us to calculate the decayed. So if original was 8 times 10 to the power of 25, then we are having the remaining as this. Then the answer now, which is the decayed. Remember, the formula gives us the remaining, but now we want to calculate the decayed. So we will need original number minus the remaining number so that we may get the decayed. So this is going to give us 7.0 multiplied by 10 to the power of 25 particles. Thank you for following. Subscribe and share.